Welcome back, everyone. We continue on the part 4 of lecture 2, slides, slides 39, example 1. Okay. First, we're talking about a linear system. Here is x1 minus x2 plus x3 equals to 3, negative x1 plus x2 plus x4 equals to 2, negative x1 plus 2x2 plus x5 equal to 6. And here we particularly simulate a constraint of a linear program when the slack variable are added into the system. We can also put it into a matrix form like this. Okay. Assuming we wanted to using x1 and x2 and x3, first threes are using the first three are as the basic, okay, just like we said it before. So these for 3 columns are basic matrix, x1, x2, and x3 are corresponding to the basic variable, x4 and x5 corresponding to the non-basics. So we can actually do a partition. We can form that, do a partition adding the right-hand side as extended matrix, perform a reduced echelon form, okay, all the way. So we can pivot and trying to form a identity matrix on the left-hand side, and the rest of them, this is what we call the non-basic. So very similar to where we had it before. So we're trying to find a B times B inverse equals to identity matrix, and this will be the B times N matrix, and this is the right-hand side. So therefore, if I said, for example, this represents what? The identity matrix of 3 times x1, x2, and x3 equals to 2, 4, and 5 minus, okay, negative 2 times x4, 1 times x5. X2 equals to 4 minus negative x4 plus x5. And x3 equals to 5 minus x4. And that's it. So here we're trying to say this x4 and x5 are free variable, x3, 1, 2, and 3 are basic variable. Okay. So this we can calculate. Once we set any value to x4 and x5, I can directly calculate the value of x1 and 2 and 3. However, it is more convenient. I'm just setting in linear programming as well. We're setting x4 and x5, and we'll force them to be 0. And then we can directly know x1 equals to 2, x2 equals to 4, x3 equals to 5. Okay, here just showing you some of the struggle I have by hand calculation and more struggle. So I'm showing you my calculation itself is hand calculation is not exactly precise, or it is a time-consuming process. I just presented the result in the slide. Look at this equation. Another one. Okay. But it is easier to pick, okay, x3, x4, and x5 as a basic variable as well. So therefore, I can actually pick this one to begin with, and x3 equals to 3, x4 equal to 2, x5 equals to 6 directly to begin with. All right, so that's fairly simple, and we can just using this matrix, this part of the x1 and x2 column, as a non-basic. So this is very straightforward. That's why we adding these so-called slack variable, so we can easily find the initial basic solution, initial feasible basic solution without involving the original variable. Okay. So give you an example of a degenerate solution. For example, this is our A times X equal to B, the constraint matrix, like that. Okay. We let x4 and x5 equal to 0, so x1, 2, 3 are the basic column. Okay, x1, 2, 3 are the basic column. Since we set the x4 and x5 equal to 0, I can directly doing the inverse matrix of this. I can calculate xb. xb says x1, 2, 3 equals to 3, 3, 0. And I filled in x4 and x5 are 0. This is my entire solution right here. However, you see that if I exchange x3 and x5 equal to 0, x4 becomes the basic solution. x4 becomes the basic solution. I will have a slightly different B matrix. This 2 column plus this column. So these 2 column plus the column corresponding to x4. And we can calculate, the right-hand side stay the same. I can do B inverse times B, getting my basic solution 3, 3, 0. I get exactly the same solution even though I switched bases. So the basic matrix is either B or B prime, They're different, but the solution is the same. We call it degeneracy. And this is usually in the case in linear programs. If we have a so-called redundant constraints, and this could happen quite a bit, so that even though you switch the bases, but you're not leaving that particular corner point or extreme point. Finally, we'll talk about the theorem of basic feasible solution. Okay. First, we're trying to say is the basis. My feasible region is bounded. Okay. X is the extreme point of S. Okay. S is equal to the y for all the A times y equals to B, and y is non-negative. So therefore, X is the basic feasible solution. First, we're going to prove the reverse direction, as we said it before, the reverse direction. So that's assuming X is a basic feasible solution equals to the XB part, which is the base part, equals to greater than equal to 0, and the non-basic variable equal to 0. So this is how we set it up. Before, we force all the non-basic variable equal to 0, and we can calculate the corresponding basic variable value. So let a U between 0 and 1, and X prime and X double prime belong to the set S feasible region. So any X belong to the feasible region can be represented as a U times X prime plus 1 minus U times X double prime. For example, what I'm trying to say that if X itself extreme point, the X prime has to be equal to X double prime since X is the extreme point. So let's take a look how this has happened. So my logic is if X is a basically feasible solution, which has this format, okay, XP times XP and 0, and then we find a so-called convex combination weight, the convex combination between X prime and X double prime representing this current point, basic solution called X. I'm trying to show that X prime and X double prime are exactly the same, okay, equals to X, basically. X prime and X double prime equal to X. So here we're trying to do the convex combination using this form, definition of a basic solution, XP and 0 equals to U times XP prime and X prime and XN prime plus 1 minus U X double prime B and X double prime N. And and this will be resulting solution is actually what we're trying to say is this part, the part down here are equal to 0. 0 equal to U times xn prom plus 1 minus u times n double prom. So we prove that xn prom and x n prom and xn double prom equals to 0. Both of them equal to 0. But look at the basic part. Basic part equals to b times xb equal to b. Therefore, b times x prom plus n times xn prom equals to b times xb prom. If I multiply both sides by b inverse, I will have xb equal to xb prom. And also equals to b times x double prom b. Okay, x double prom b. If I multiply both sides by b inverse, and xb will equals to xb. So we have shown the reverse direction. If x is the basic feasible solution, basically the current point x equals to x prom and equals to x double prom. So this is meaning there's no way I can find two other extreme points to represent the current solution x as a convex combination. Second, if xb is x is an extreme point, remember, so that only the first p entry of x are positive. Therefore, ax equals to b becomes the p j equals to 1 to p, and actually xj times aj. Aj is the column of rows of a equals to b. We must show that a1 to ap are linearly independent. So here we're trying to show that a1 to ap are linearly independent. So this is by contradiction. Okay? By contradiction, what we're trying to show is if this is the direction we're trying to prove that some of the AJs are not linearly independent. So assuming they are linearly independent, so based on the linearly dependent definition, there are RJs not all 0. If I represent R times AJ, RJ times AJ for all the P of AJ equal to 0, some of the RJ are not equal to 0. Okay, since x is greater than 0, xj equal to 0 for all these p, since they are positive number, there exists a u small enough, and x prom equals to xj plus u times rj for all the p. And also small enough to find that xj double prom equal to xj minus a certain rj. So both x prom and x double prom, since u is greater than 0, x prom and x double prom are different. We can also represent x equal to half of x prom and half of x double prom, since this part and that part can be canceled out. See what I'm saying? So we can prove that actually the x is not an extreme point by definition, because we can find a x prom and x double prom, they're different by this much. Okay? 2 times mu times rj, and therefore we can prove that x is not an extreme point. So the proof is a little bit more formal, but here what we're trying to do is, if that's the case, if A1 to AP are linearly dependent, we can always find two other two other points using their convex combination to represent the current solution. So the current solution is not a basic feasible solution. Solution is not basic. Okay, so therefore it's not an extreme point in that case. All right. So this we can show that the theorem of a basic feasible solution shows a set of x s is a set of x, ax equals to b, x is non-negative, s is not an empty set. The row rank of A is equal to m. Then A times x has at least one basic feasible solution, at least one extreme point. So that's what we're trying to prove. Set x be a feasible solution with m plus 1 positive variables. So in that case, we can always choose that xj minus u times rj times a equals to b, and also xj times aj equals to b, and summation of rj times aj equal to 0. So x minus uj is a feasible solution with one less positive number of variable, so we can show that. So for example, this is the case. Currently I have 3 current solution is 1, 1, 1, and 0. And the R equals to 3, 4, negative 1, and 0. A matrix equals to that with the row rank is 2. Okay, 2 rows, row rank is 2. So here we have 2 row rank of 2, but we have 3 positive solution, basic solution. In this case, it's not even basic solution. 3 positive value in current solution. So we can find a 1 times 1, 0, which is the first column, 1 times second column, 1 times the third column, and 0 times the fourth column equals to 4 and 5, which is the right hand side. Okay. Second, we can do 3 times the first column, 1, 0, 4 times the second column, negative 1 times the third column, and 0 times the fourth column equal to 0. So multiply the second equation by a u and subtract it from the first equation, and we can get the same solution. So therefore, we can find a 1 less, okay, so if currently is 1, 1, 1 minus 3u, which is 3u, second is 1 minus 4u, okay, 4u, and 1 plus 1u, okay, greater than 0, we can form the range of u. U has to be less, for the first equation, u has to be less than 1/3. Second equation, u has to be what? Less than 1/4. The third equation says u has to be greater than negative 1. So overall, what we have, u has to be between negative 1 to positive 1/4. Okay? So either we choose u equals to 1/4, and we can form another basic feasible solution called 1/4, 0, 5/4, 5/4, and 0. That's one less non-zero solution. If we plug in u equals to negative 1, x minus u times r equals to 4 and 5. So we can always find the ax equals to b with one less positive variables in my solution. So it's just a numerical illustration. How can we do that? If we can find r, which is the r is r times aj, r times all the columns in the A matrix are equal to 0, which means these r vectors is perpendicular. R vector is perpendicular to all the columns space. So this concludes the lecture 2 and proving sum of theory In the next lecture 3, we're going to using some of these theorem of basic feasible solution, the theorem of polyhedral set, and we construct a so-called simplex method fundamentals, and then we're going to start talking about how we simplify this current simplex method as for implementation based on this knowledge we learned in this lecture. Okay, we'll see you in the next lecture.